All right, let's talk about one of the most important chemicals on the planet, ammonia. We're going to dive into a fascinating blueprint for a totally new and maybe revolutionary way to make it.
And when I say important, I am not kidding. This stuff literally feeds the world. It's the key ingredient in the fertilizer that grows our food. But the way we've made it for over a century, it's effective for sure, but it's an absolute energy hog, requiring super high pressures and temperatures.
So you gotta wonder, right? Is there a better way? What if we could whip up this essential chemical with just the simplest things imaginable? Literally air, water, and a bit of electricity. That's the big idea we're gonna unpack.
So here it is, the proposed reaction, the new recipe. You take nitrogen gas, the stuff that's all around us in the air, add some plain old water, and the goal is to get ammonia, with a little oxygen gas as a byproduct. Looks great on paper, but the real question is, does it actually work?
To figure this out, we're gonna put on our chemist hats and deconstruct this blueprint piece by piece. Let's not think of this as some boring textbook problem. Nope. Think of it as our mission.
And this mission has 3 key parts. First up, is this thing even energetically possible? Do the laws of chemistry allow it? Second, what kind of machine do we even need to pull this off? And finally, the big one, how well does it actually perform in the real world?
Okay, let's tackle part 1, energy. The fundamental question here is, does this reaction just happen on its own, or are we gonna have to give it a major push to get it going? To get to the bottom of that, we have to talk about a really important concept.
And that concept is called Gibbs free energy. The easiest way to think about it is like this. It tells you if a chemical reaction is a downhill slide or an uphill climb. If the Gibbs free energy number is negative, it's all downhill. The reaction just happens spontaneously. But if it's positive, well, you've got an uphill battle on your hands, and you're going to need to pump in energy to make it go.
So, for our ammonia reaction, what's the verdict? Well, the number is a big, fat, positive 678.5 kilojoules per mole. That plus sign tells us everything we need to know. This isn't just an uphill battle. It's like trying to push a boulder up a mountain. It is absolutely not going to happen by itself. We have to force it, and that means we need a power source.
Okay, so we know we need to pump in energy, but how much electrical energy? How much voltage do we need from our power supply? Luckily, there's this fantastic little equation that acts like a bridge, connecting the world of chemical energy, that's our delta G degree, to the world of electrical energy, the E degree, which is basically the voltage we need.
It's actually a pretty straightforward calculation. First, we need to count how many electrons are getting passed around during this reaction. Once we have that number, we just shuffle the equation around a little, plug in the values we know, and boom, it'll spit out the minimum voltage required to get this thing started.
So where are these electrons coming from? Well, if we break the reaction in half, you can see it's like a little dance. At one end, called the anode, water gets split apart, and in the process, it releases 6 electrons. Then, over at the other end, the cathode, nitrogen gas grabs those same 6 electrons and uses them to become ammonia. It's a perfect handoff. And that number, 6, is exactly what we need for our formula. So N equals 6.
Okay, enough with the math and theory for a second. What does the actual setup, the machine that makes this all happen, really look like? Let's take a peek inside the lab.
And here it is. This is called an electrolytic cell. Now, it might look a little complicated, but it's really just a couple of containers, each with a metal strip called an electrode, connected by this thing called a salt bridge. And that power supply? That's the muscle. That's what's providing the electrical push to make our uphill reaction actually happen.
So let's zoom in. On one side, at the anode, that's where the water is breaking down and bubbling off oxygen gas. And over on the other side, at the cathode, that's where the real magic happens. Nitrogen gets zapped with electrons and turns into our final product, ammonia. So, we've checked the boxes, we know it's possible if we pump in enough energy, and we know what the machine looks like. But now for the moment of truth, the most critical part of this whole investigation, the reality check. How much ammonia do we actually make?
You know, there's this great saying, in theory and practice are the same. In practice, they are not. And boy, is that true in chemistry. What you calculate on paper is almost never what you actually get in the lab. There's always something that gets in the way.
So, here's the plan. First, let's figure out the best-case scenario, the theoretical maximum. We'll take the amount of electricity we used, the current and the time, and calculate the total number of electrons that flowed through our cell. From there, it's some simple chemistry math to figure out the absolute most ammonia we could have possibly made.
Okay, the numbers are in. On paper, based on all that electricity, we should have made about 0.0124 moles of ammonia. That was our theoretical goal. But what did the experiment actually produce? Only about 0.00105 moles. Yeah, that's a pretty big difference between what we hoped for and what we got.
So let's turn that into a percentage. We just take the actual amount we made, we divide it by the theoretical maximum we could have made, and what do we get? The final efficiency of this whole process is a mere 8.4%.
Let me put that another way. For every 100 molecules of ammonia we should have made, based on the energy we used, we only got about 8. That's it. That means over 90% of our expensive electrical energy just went somewhere else. It either made other things we didn't want or just got wasted as heat.
So what did we learn from our little mission here? Well, first, the good news, making ammonia from just air and water isn't science fiction. It is chemically possible. The bad news, it takes a ton of electricity to do it. And the really big takeaway, the efficiency, right now, is pretty terrible. And that's the #1 roadblock standing between this cool idea and it actually changing the world.
And that leaves us with the big final question, doesn't it? When you see a number like 8.4%, do you call it a failure? Or is it actually a success? Is it proof that the concept works, even if it's not very good yet? Is this the critical first step on the path to a real food revolution, one that just needs better science and engineering to get that number way, way up? Well, that's the puzzle scientists are trying to solve right now.